Okay guys, we're going to try this again. I've done it a billion times and then I always get interrupted by my daughter. So if you hear her, I apologize. I'm just going to try to keep going this time or else I'll be here all day. Okay, so we were talking about heat. Okay, we were talking about the transfer of heat between materials. Remember, you have convection, conduction, radiation. We just talked about specific heat. So in my last notes, we said that specific heat is specific to every kind of material, and it's how much heat is needed to change the temperature of 1 kilogram of that material by 1 degree Celsius. Remember, some materials are good conductors of heat, which means that they don't require a lot of heat energy to change their temperature. Metals are good examples of conductors, whereas you have some materials that are insulators, so they're going to require a lot more heat energy. It's going to take a lot more time and heat to get them to change their temperature. Water is a good insulator. It takes a lot of heat energy to change the temperature of even just a small amount of water. Okay, this particular lab is called a calorimetry lab. And so what it does is, this is called a calorimeter. Okay, and so what it does is, this is a temperature probe right here, and so it would record the temperature of the water that's in here. So if I'm looking at this, okay, I can see that I have 30 grams of water, and I can see that the initial temperature of the water starting off right now is 20 degrees Celsius. Okay, they're also telling me that the specific heat of water is 4.18 joules per gram degree Celsius. The reason that we had 4,184 joules per kilogram degree Celsius is because they're using grams, we use kilograms. The only difference is that that's all they did. Okay, they just changed the value here to reflect the fact that they're talking about grams instead of kilograms. Okay, so I can see that the initial temperature of the water is 20 degrees Celsius if I have these different metals here and I heat them up. So in this case, I have silver, gold, copper, iron, and I also have 2 unknown metals. I can see the mass of those different materials, and then I can see the initial temperature. In this case, okay, the initial temperature of the water and the initial temperature of the metal is going to be the same. So what do you think is going to happen when I put this piece of metal into the water if they're both starting off at the same temperature? Do you think that you're going to see a temperature fluctuation in either the water or the metal? And the answer to that would be no. Okay, you might see a slight change here, okay, but it's not going to be very much. And again, that's because they're already the same temperature. Remember, heat flows from hot to cold. So if one of them was hotter than the other, then heat is going to flow from that particular object into the colder one until they're the same temperature, until they've reached their equilibrium. So if I were to reset this, and let's say I use silver and I increase the temperature of my silver to, let's say, 220 degrees, well, now that piece of metal, that silver, is a lot hotter than the water that I'm going to be putting it in. So I'm going to see that heat from the metal is going to flow into the water. Remember, heat flows from hot to cold until they're both the same temperature. So you're going to see that this initial temperature of the water, which is 20 degrees Celsius, is going to change. It's going to increase. It's going to get hotter because heat from the piece of silver is flowing into the water until they're both the same temperature. So what this temperature probe is doing is it's saying, okay, I'm looking at the temperature change in the water. In this case, I can see that the temperature is increasing because of the hot piece of metal that you put in there. Okay, and I can see that at some point it's going to start to even out. It won't ever stop. So you can just kind of guesstimate. So in this case, I would say it's about 27.19 degrees Celsius. That would be the final temperature of the water. And in this case, that's also the final temperature of the piece of metal itself. So the piece of metal decreased its temperature. It went from 220 degrees Celsius to 27 degrees Celsius, whereas the water increased its temperature from 20 degrees Celsius to about 27.19 degrees Celsius. So there was a transfer of heat from the metal into the water. Okay, once I select a particular metal, I can also see that they're giving me the specific heat of that metal. In this case, the specific heat of silver is 0.234 joules per gram degree Celsius. I can do the same thing with any of these other materials as well. So if I were to take gold, again, I can start off with 20 grams of gold. If I just leave the temperature alone, it's going to start off at 20 degrees Celsius. I can see that I have 30 grams of water, and I can see that my temperature and my initial temperature of the water is 20 degrees Celsius. So if I were to drop this piece of gold into the water, I'm not going to see a change in the temperature of the water because they're already the same temperature. So if I were to drop this in, you're going to see that the temperature of the water is going to stay relatively the same. Again, the only time that you'd see a change in the temperature is if you're seeing a heat flow from hot to cold. In this case, there is no heat flow because they're both starting off at the same temperature. Okay. If I were to increase the temperature, okay, of my gold, you're going to see that the temperature of the water is going to again increase because heat is flowing from the piece of gold into the water until they're both the same temperature. So you would do this with all of these metals. Okay, so again, you can just let it run, give it a few seconds, it'll eventually stop increasing. Okay, and then you can just kind of guesstimate. So for this particular value, I'd say that the temperature would be like 23.98, 23.99 degrees Celsius. So that would be the final temperature of the water, and that would also be the final temperature of the metal itself. Okay, so what you're going to be doing, and I hope that this works out for you, is you're going to be drawing a graph that looks something like this. So here are the different metals. So you have silver, gold, copper, iron, and then you have your two unknown metals. Okay, you're going to leave the mass at 20 grams, and you're going to increase the temperature of the metal to the 220 degrees Celsius. The water here, I filled that out for you. So you're starting off with 30 grams of water. That's not going to change. And the initial temperature of the water is always going to stay at 20 degrees Celsius. Once you drop that hot piece of metal into the water, again, you're going to see that change in temperature occur. So you're going to fill out, okay, the change in temperature T2 for those different, for the water when you drop in the different metals here. So let's go over the first one. So let's do the first one again. Okay, so for silver, okay, I'm changing its temperature to 220 degrees. If I can get this to work. There you go. And I'm going to start it off. Again, give it a couple of seconds, but I can see that the temperature of the water is increasing. Okay, it's doing it rather slowly, but you can still see nonetheless that the temperature is increasing. Eventually, it'll level out, okay, and it'll stop increasing. In this case, I say that the final temperature is about 27 point, I put 27.19, you can put 27.2, whichever one you feel comfortable, you're going to get close to the same answer. Okay, so in this case, I'd say the final temperature of the water and the final temperature of the piece of silver is about 27.19 degrees Celsius. So if I go back to this, okay, I'm going to put here that the final temperature is 27.19 degrees Celsius, and the final temperature of the water is also 27.19 degrees Celsius. Remember, once they've been sitting in each other, so once the metal has been sitting in the water for some time, the temperature will eventually even out, and they're going to both be the same temperature. So the temperature of the silver and the temperature of the water at the end of that is going to be the same. Then from there, I can go and calculate how much heat energy in this case was gained by the water. So remember, the water increased its temperature. It went from 20 degrees Celsius to 27.19 degrees Celsius, which means that it increased its temperature, it gained heat energy. So remember, the formula to calculate heat energy is the mass times the specific heat of the material times the change in temperature. So in this case, I have 30 grams. Okay, you're not going to, in this example, you're not going to have to change it to kilograms because the value of the specific heat that they're giving you is in joules per gram degree Celsius. If this was joules per kilogram degree Celsius, the value would be 4,184 joules per kilogram degree Celsius. In this case, they converted it. So for this particular virtual lab, you're not going to have to make the conversion to kilograms. Okay, so it would be 30 grams times the specific heat of water, in this case it's 4.184, times the change in temperature. Well, my change in temperature, remember, final minus initial, so it's 27.19 minus 20, which gives you a change in temperature of 7.19, so it's 30 times the specific heat, 4.184, times the change in temperature of 7.19, and you get heat energy of 902.49. Again, you can stop this video at any time and you can go ahead and make your calculation and see if you got it right. So this was how much heat energy was gained by the water. Remember, it gained this amount of heat energy because the temperature increased. That amount is equal to, okay, how much heat energy was lost by the metal. So since the metal was decreasing its temperature, it went from 220 degrees to 27.19 degrees Celsius, it lost heat energy. How much heat energy the water gained is equal to how much heat energy was lost by the piece of metal. So in this case, it lost a negative, we say negative because it lost that amount, 902.49 joules of heat energy, so same thing. Okay. And now I can use one of my rearranged formulas, okay, to solve for the specific heat of silver. I already know what it is because if you go back, okay, it tells you the specific heat here is 0.234, okay, but you can check your values or you can check your answer just to make sure. So if you look at the rearranged formula, okay, to solve for specific heat, it's your heat energy divided by your mass times the change in temperature. So again, to solve for specific heat, the rearranged formula is heat energy divided by whatever your mass is times the change in temperature. So in this case, it would be 902.49 divided by 20 times this change in temperature, which is 192.81 degrees Celsius. And if you do that, you get a value of 0.234. And again, that's the specific heat of silver. If I were to check it, okay, you would have gotten the same thing. So if I do the same thing, so if I reset and do the same thing with gold, okay, and I go back to my data table, my gold, the mass is 20 grams. My initial temperature of the gold, I'm going to increase it to 220. And again, I can see that the amount of water that I have is still 30 grams and the initial temperature of the water is still 20 degrees Celsius. So again, if I drop that hot piece of gold into the water, I'm going to see that the change in temperature of the water is going to increase. It's going to get hotter until, okay, they're the same temperature. So again, I'm going to kind of let it run for a bit. So you can see the temperature continues to increase. Okay, at some point, that temperature is going to stop increasing and it's going to stay relatively the same. So in this case, hey, it stays about 24. I leave it at 24.0, so that's what I put it as, 24 degrees Celsius. So the temperature of the water increased from 20 to 24 degrees Celsius, and the temperature of the metal decreased from 220 to about 24. So if I go back to my chart, hey, the final temperature of the metal was 24. And the final temperature of the water was also 24 degrees Celsius. So again, I can calculate how much heat energy was gained by the water. Again, the water increased its temperature, so it gained heat energy. So that would be heat energy, Q, is equal to the mass, 30, times the specific heat, in this case of water, times 4.184, times the change in temperature, T2 minus T1. So how much did the temperature change by? It went from 20 to 24, so that's a difference of 4. So if I have 30 times 4.184 times 4, that was my change in temperature, I get a value of 502.08. Okay, that's how much heat energy was gained by the water. Then that value is the same as how much heat energy was lost by the piece of metal. So 5 negative, in this case it's negative because it lost it, 502.08. And then again, I can use my formula to solve for specific heat. So remember, specific heat is heat energy divided by the mass of the material times the change in temperature. So in this case, the change in temperature was 220 minus 24. Okay, so that's a difference of 196 degrees. So it would be 502 divided by 20 times the change in temperature of 196, and you get a value of 0.128. Okay, that's the specific heat of gold according to your calculations. And if you were to check that out, you get that same number. So they're telling you the specific heat of gold is 0.128 joules per gram degree Celsius. Again, that's a known value. That's always going to be the specific heat of gold. So go ahead now and try to do the same thing for copper, do the same thing for metal, and then try to get the specific heat of metal X and metal Y, doing the same steps that we just did now. Again, I'll be here to answer any questions. Just send me an email. Stay healthy and good luck.